All right, so at long last, we're going to do some computations, and we'll do these in the context of the Serre spectral sequence. So let's do this for cohomology. We'll have the E2 page is the cohomology of the base with coefficients in the cohomology of the fiber, converging to the cohomology of the total space. So this is in the usual setup where F to E to B is the fibration. And I must be assuming that pi1 of the base acts trivially so that I don't have to worry about local coefficients. And we saw in the last video that Eilenberg-MacLane spaces, together with the loop path fibration, give us a nice source of fibrations. So let's do an example with one of those. So here I'm taking the loop path fibration on KZ2. Paths on KZ2 are contractible, and then the loop space is again an Eilenberg-MacLane space, and we saw last time that it should be KZ1. So I've got this loop path fibration, and KZ1, of course, we know a model for, so we could take this to be S1, and it turns out KZ2, I don't know if people know this or not, but a model for this is CP infinity. But we're going to go through this computation assuming that we don't know that, just to sort of get our feet wet in how this kind of stuff works. And then we'll do more complicated things where maybe we don't actually have a nice model next. Okay, but in particular, whether we know it's CP infinity or not, KZ2, we know all the homotopy groups. So our base is simply connected here. So pi1 is 0, and that tells us that we don't have to worry about local coefficients when we look at our Serre spectral sequence. And what does that Serre spectral sequence look like? Well, the E2 page, I guess it's going to be the cohomology of the base, that's our KZ2, with coefficients in the cohomology of the fiber, that's KZ1. And then this should cook up for us the cohomology of the total space, but that's contractible, so it's just a point. And that's, of course, 0 unless P plus Q is equal to 0. Okay, and we're going to be working with the first quadrant spectral sequence, so that's really only when P is 0 and Q is 0. Also notice that the cohomology of S1 we know, which is a z in degree 0 and a z in degree 1, and so that's free as a z module, right? So we actually have a spectral sequence of algebras because cohomology is a ring when we're using integral coefficients. And we know that E2 page is actually going to split up as the tensor product of the cohomology of the base and the cohomology of the fiber. Okay, and we'll see how that plays out in a moment, but now I want to get this computation started. So let's take a look at the E2 page. And I'm going to put P on the horizontal and Q on the vertical. So I always like to remind myself over on the Q axis, I should have the cohomology of the fiber. And on the P axis, I should have the cohomology of the base. Maybe let me give myself some numbers here. Whoa. Sliding all around. Okay, in theory, working on this grid is supposed to help, but I find that I need to separate these anyway. Graph paper really helps with these computations, by the way. So here's where the p-axis meets the q-axis. Okay, and what I'm supposed to put here is the cohomology of the base with coefficients in the cohomology of the fiber. Okay, maybe I should write that off to the side. We know the cohomology of our fiber because it's just the cohomology of S1. So we have Z in degree 0 and Z in degree 1. And when we're looking at the first column, that's H0 of the base. Well, our base is connected, so H0 should be the integers. And then we should be doing that. Well, it would be the integers if we're doing integral coefficients, but H0 of S1, our fiber is also integers. So yes, that should be a copy of the integers. And in the 0, 1 spot, right above that, we're taking the cohomology, the 0th cohomology of the base with, again, coefficients in the integers, because each one of the fiber is also Z. So that's, again, the copy of the integers. And we've got 0 all above here, because we're taking the cohomology of the base with coefficients in 0. Okay, so this is what we have so far. I guess let me say a little bit more. So the cohomology of the base, well, we know the base is simply connected, so we also know H1 should be 0 in any coefficients, and that's true here too, and we've again got zeros up here. In fact, I can extend these zeros up here because the coefficients we're using are 0 once we're up there, so there can't be anything at all. Okay, and maybe let me also remind you that we're looking at the dr differentials in this setting have by degree r, comma, minus r plus 1. And we're starting on the E2 page, so I'm really only interested in r being greater than or equal to 2. I don't care what happened on the E1 page, and I won't have any D1 differentials. Okay, so this is what we know so far, assuming that we don't know the cohomology of the base. We just know that it's simply connected. And what we're supposed to end up with is we're supposed to converge to the cohomology of a point. So we should have this one copy of Z in degree 0, 0, and then this other copy of Z needs to die. Right? Because we shouldn't have any higher cohomology at the end of this whole process. Okay, that's not to say it has to die on the E2 page. It just needs to die eventually. But remember, we often play this game where we draw all the pages at once. So I'm drawing the groups that are on the E2 page, but maybe we'd have some higher differentials here too. Okay, I'll say more about that as we get there. But in this situation, I'm making a big deal out of nothing, because when I look at this copy of the integers, if it has to die, well, there are no differentials coming into it because this is all 0 over here, right? This is the first quadrant spectral sequence. So the only way we could have a differential out is, well, a D1, nope, we're past that, we're on the E2 page. So the only possibility is a D2. So we must at least have a copy of the integers here for this copy to inject into, so that when we take kernel mod image at that spot, we get 0. Oops. Okay. All right, so there's at least a copy of the integers here in the 2, 0 spot. But now what does that tell me? That tells me that H2 of the base with coefficients in the integers is a copy of the integers. And then right above that Z that I just wrote, I again write H2 of the base with coefficients in the same thing. So this must be exactly the same. Okay, but now, as it stands right now, these two copies of Z will kill each other in homology, right? Here I'll have the kernel is 0, but then the image is all of Z, so I'll end up with nothing there. And nothing is coming into this, and the kernel will be nothing on the E2 page. If this is an injection, I guess let's maybe mark that as an injection. And so right now those groups are fine, but this new copy of the integers needs to die. Okay, so how do we kill that one? Well, I see, let me keep pointing, I see that a differential coming into it would have to come from here, but that's 0. And so the only way we can have a differential out is if there's a d2 differential, because d1 would have been the previous page, that's long gone. And d3, well, that's going to land us outside of the range of any interesting groups. This is the first quadrant spectral sequence. Okay, so the only possibility is that there's at least a copy of the integers here, and this map, again, a d2 differential. Okay, and as soon as I've got that, well, now I know that the cohomology of the base has something in degree 4, and this was with integral coefficients. The line above it is again with integral coefficients, so I just repeat. And I'm going to stop saying this argument. You just continue. You're going to see the same kind of pattern happening here. Maybe let me at least put this here. Okay, so from this, I start to learn about the cohomology of the base, and it looks like what we're seeing here is that the E3 page is the E infinity page, because we've only written down D2 differentials. So our spectral sequence collapses after the E2 page. Okay, I think I left something out, so let me say why I have a 0 here. Oops, that's not what I meant to do at all. I meant to point. So why do I have a 0 here? Well, if I had something non-zero here, then the only place it could receive a differential from is here or here, and there's nothing there. Okay, and then the differentials out already go off the outside of the interesting range, outside of that first quadrant. So actually I know that this is a 0. And then I just repeat up above, that must be a 0. And I can play the same game here, and then it repeats, and so on. So it's not just that it appears that we only have D2 differentials. Indeed, we only have D2 differentials, and this pattern will continue. And so our E3 page is our E infinity page, and our spectral sequence collapses. Okay, I guess this already tells me that I know the cohomology of my KZ2 space, which is the base here. Well, it looks like I'm only going to end up with Z in even degrees and 0 in odd degrees. But I can actually say more. So let's think about this spectral sequence again, but as algebras, or as a spectral sequence of algebras. I guess I'm going to need a new page. So I'm going to draw the same thing again, but keep track of the algebra structure. Let's maybe go a little further so we can see more of it. Okay, again, I'm drawing the E2 page, and here's sort of my 0, 0 corner, so I'm going to draw that up and to the right. We already know the cohomology of the fiber, because it's the cohomology of S1. What is that as a ring? Well, we could call this 1, that generator, and then the generator in degree 1 we could call X. Okay, and then I guess X squares to 0, because we know we've got 0 up here. And the same argument as before gives me zeros all the way over here. Our base, remember, was simply connected, so I've got zeros here. And then the first stage, we said there has to be a copy of the integers here to support a differential. And let's just name the generator of that. We'll call it Y. Well, now remember that our E2 page should be the tensor product of these rings, the cohomology of the fiber and the cohomology of the base. And so in the tensor product I should have a class that looks like x times y. And so here, that copy of the integers is just generated by x times y. Okay, well, we saw that there should be a copy of the integers here that supports a differential. And we can compute that really explicitly because once we know that d2 of x is y, and also we know x squares to be 0 just because we know the cohomology of S1, now using the Leibniz rule, we can compute d2 of xy. Well, that should be d2 of x times y. And then it's plus or minus, so the degree depends on the class you're moving the differential past. And that x is in degree 1, so that's minus. I just mean it's in an odd degree, so that's minus x d2 of y. So that's my Leibniz rule. Now y was on the p-axis, right? So that can't support any differentials because we'd land in outside of the first quadrant. So that was definitely 0. And so we see that d2 of xy is just d2 of x times y, which means we're getting y squared. Okay, so y squared is the thing that could have lived in degree 4, and in fact, we could take it to be the generator of this copy of the integers that gets hit by this other copy. Okay, now we can continue to play that game. So once we know this copy of the integers here, we know there's one right above it because we're using the same coefficients. And thinking about this as the tensor product, there's a class there that looks like xy squared. And we look at the differential on xy squared. Same game, we have d2 of x times y squared minus x d2 of y squared. That y squared, again, lies along the edge, so it doesn't support any differentials. And we've just got y cubed. And so we can call the generator of this copy of the integers y cubed. Okay, and now there's a z generated by x y cubed, and we continue. All right, also for degree reasons, as before, if I look in this spot here, then the only place I could have a differential is from here, or if it were a d2, or maybe here if it were a d3, and there's nothing there. So this must be 0, and that makes that 0, and we can play the same game here and here. Maybe let me actually say it for this one. Got something here. It could only be hit by a differential, a d2 coming from here, or a d3, or a d4, or a d5. Those are all 0. So again, 0. Okay, so what have we learned here? We've actually learned that the cohomology of our KZ2, it's not just z in even degrees. We now know as a ring, it's just going to be z adjoin y. So this pattern just continues, and we just get higher and higher powers of y, and this is for y in degree 2. Okay, and if you think about the cohomology of CP infinity, that checks out. That's precisely what we should have, is polynomial on a generator in degree 2. Okay, so this is sort of the simplest version of a computation, and so far we've really only recovered something that we already know. But in the next video, we'll look at a much more complex computation and actually learn something new.